Now, when we excite certain elements, so here I have a high voltage EHT power supply, and I have a small amount of a gas which we're going to basically excite, what we find is that only certain frequencies of light are emitted, and these correspond to the energies of certain photons. But why is it that sodium and the other kind of things like mercury, oxygen, why do they only give out a certain colour of light? Well, the reason is all due to the energy levels that we have inside that particular atom. But before we look at that in a bit more detail, I'd like to look at things that we call spectra. Now, they're basically three main types. We have continuous, emission, and absorption. Now, here we have a continuous spectrum. I mean, I made it out of Lego, so it's a bit blocky, but effectively this is our kind of beautiful rainbow of colours that goes all the way from red all the way through to violet. So Richard of York gave battle in vain. And basically this has every single frequency of light that we can imagine. It's the kind of thing that we get if you maybe heat up some metal, maybe a metal filament, so a filament kind of lamp bulb. What this does is it gives out a continuous spectrum, and therefore it has every single frequency of light. But as we saw in the video, when you heat up certain individual gases made out of one element, what we then have is an emission spectra. So this is maybe the emission spectra for something like sodium. Now, sodium light, when you excite it, perhaps using high voltage, it only gives out maybe orange and yellow light. Now, our eyes sort of see the kind of two colours of light all combined, but basically if you excite a gas, the electrons inside the different energy levels drop down and they only emit certain frequencies of light. So this is an emission spectra. However, we also have like the kind of negative image of this, and this is what we call an absorption line spectra. So if you have some cool gas, perhaps maybe we can again have some sodium gas. If you have some cool sodium gas and you pass white light through it, or a continuous spectrum of colours through it, this gas will only absorb certain frequencies of light, and effectively it lets everything else through, but it takes in certain frequencies of light. And this is what we call an absorption line spectra. Now, every single atom has its own particular sort of spectra, and it depends on how tightly all of these electrons are sort of bonded into that nucleus. Now, if we imagine some kind of element, perhaps element X, what we find is the electrons only exist at certain quantized energy levels. So you excite the gas and the electrons move up. When they lose their energy, they drop back down to their ground state. And dependent upon the size of the energy gap, this tells us the amount of energy given off. Now we know that the amount of energy given off is equal to HF. That's the frequency of the emitted light of the photons that come off. And what we find is that there's only going to be certain colours of light given off. If it's sodium, for example, what we find is that there are distinctive photons given off. Perhaps we have some orange light and some yellow light. And that's why with sodium, we see it glowing as a sort of lovely kind of orange colour. Different elements obviously have different kind of energy levels. When it comes to looking at the absorption line spectra, well, effectively, this electron here can only sort of absorb certain quantities of energy. It can take in just, this amount of energy to get to this level, just enough to get to this level, or to drop down by, this level over here. And really, what we're talking about is any photons which don't have quite the right amount of energy just pass straight through this and are not absorbed. So if you have maybe quite a low energy red photon with some sodium, if this electron here sees this red photon of light, it's not quite enough energy to get up to the next state, and therefore it doesn't move at all. And therefore the red photon of light moves straight through. And this is why we really have these absorption spectra. These are really useful if you have maybe a source of different coloured photons. So perhaps we have a red, orange, yellow. Just going to get a green one over here, and also maybe a blue one. Oh, a bit of onion skin there from another video. Right, so basically if you have a load of photons that hit a load of sodium gas, which is kind of a cool gas, only certain photons are absorbed, and the orange and the yellow are absorbed, which means any red photons, green photons and blue photons pass straight through. What happens to these photons? Well, these photons of energy, what they do is they cause the electrons to be excited to another energy level, and then when they drop back down to the ground state, these photons are emitted in all directions. They're emitted in 360 degrees in a kind of perfect sphere. So a small amount of energy will be absorbed, will be emitted in this direction, but a very, very small fraction of it. So what we then tend to see is we see all of the red light passes through, we see the green light and the blue light as well, but certain frequencies of yellow and orange light are absorbed, and that's why we see this kind of absorption line spectra. I hope that makes sense. I've got a couple of other videos on my other channel which I made over a year ago. You know, they've had quite a lot of hits, so hopefully that sort of makes a bit more sense as we think about emission spectra, the light given off, or absorption spectra, which are the colours of light which are absorbed by different elements. And by the way, this is really important. We need to know about this when it comes to looking at redshift as we actually investigate the light from different stars. Just by looking at a star, by looking at the kind of light emitted, we can tell what's in the atmosphere, as well as, you know, how fast that star is recessing, or that galaxy is recessing away from the Earth. So I hope that makes sense. Good luck. Thank you.